Hi everyone. In this clip we'll look at the whole class of 1D kinematics problem in which one object is ahead and a second object is trying to catch up. So here's the specific problem that we will use. A world-class marathon runner maintains a pace of 3 minutes 20 seconds per kilometer as she passes in front of a cyclist in charge of providing energy gel. The cyclist waits 3 seconds and then accelerates at 2 meters per second square until catching up with the runner. Part A, how far will the cyclist need to travel before reaching the runner? And part B, what is the speed of the cyclist at that moment? If you've never tried this problem, I encourage you to do it. Remember the main steps. First, we want to model the problem. Second, visualizing it. Third, solving. And finally, in the fourth step, make sure you assess your answers. Okay, so take the time to take a look at it and then come back. All right, hope it was successful. So in here, the first thing is to model. The modeling is not very complex. Okay, we'll be assuming that all humans and bicycles are particles in here, so we don't have to worry about legs and limbs. We're assuming that there's a constant speed for the runner and that the acceleration is constant for the cyclist. So now we're ready to start to visualize the problem, which is the key step. First, I would like just to draw a motion diagram for the two. So we have the runner, and its motion diagram is fairly easy to figure out, okay, since the speed is constant. So what we have is just a woman that is moving always with equally spaced dots so that we know it's at constant speed. So we would have 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds, 5, 6, 7, and 8. And in the meantime, we also have the cyclists, and the cyclist is actually staying still for the first 2 seconds. So the dots 0, 1, and 2 are actually in the same place. And then the cyclist starts to speed up. So what we'll get is that the distance between the points will get bigger and bigger. And here we have point 3, point number 4, point number 5, 6, 7, and 8, and how wonderful they are at the same place for the 8 dots. So basically in here, roughly at about 8 seconds. Okay, don't put too much credit on the numbers in here, it's just to show you what's going on. Okay, so that's the first way of picturing what's going on, but you can also think about this in terms of the motion graphs. The motion graphs. So for instance, the easiest one usually is to start with the acceleration versus time graph. And in here, for the acceleration, we just have that the runner. And for the runner, I will be using the green line. So the runner is just moving without an acceleration, okay? Because we know the runner is moving at constant speed, while the cyclist is actually moving with a constant positive acceleration because we know that the cyclist will be speeding up. We can then look at the velocity versus time graph, which will be a little bit more interesting. And for the velocity versus time graph, in here, we are dealing with two types of curves. First, there is the curve of the runner. Okay, we know that the runner has a constant velocity. So we'll just have a flat line in here. That's the velocity of the runner. While for the cyclist starts from rest, and then the cyclist will go faster and faster and faster. Okay, so we'll have a curve that will look like this for the cyclist. And where it becomes interesting is when we look at the position versus time graph. Because here we have 2 points of view that we can take. And actually, I kind of made that decision already in the previous graph, but I will explain it now. When we look at this, we have to decide what is our t is equal to 0 corresponding to. Okay, you have two choices in here. You could say that t is equal to 0 is the moment when the runner is passing in front of the cyclist, and this will mean that if you do that choice, your initial position for the runner will just be 0, but a slightly easier way to do it is to take t is equal to 0 seconds when the cyclists start. Okay, and what you have to understand if you make that choice is that in that case, this means that the x initial of the runner will not be equal to 0. There will already be some distance traveled. Okay, so if we do this, then for the runner, we would just have that initially there's already some distance that is traveled. We can figure this out later, and then it will increase gradually like that. While for the cyclist will start from the origin and will follow a parabolic path, or I'm sorry, the graph in here will be parabolic, and eventually we have that point in here, which is the point where they meet, and that's what we're after. So keeping the position versus time graph and the indication of how we decided to choose R0, let's just list our variable. So we'll have two sets of variable to list. We will have a first set to list for the runner and a second set of variable for the cyclist. Okay. It's not very surprising what type of variables we'll be dealing with in here. So we'll have the initial position of the runner. We'll have the final position of the runner. We have the initial velocity of the runner. We have the final velocity of the runner, the acceleration of the runner, and the time interval that we are looking for. For the runner, that's a bit overkill because we know that the acceleration is 0. So that the final velocity will be the same as the initial one. Okay? And we can actually find this value. We know that the velocity of the runner, that I will just call Vrx from now on, is such that the runner, she's doing 1 kilometer in 3 minutes and 20 seconds. So we can do this calculation, and what we get is that we have 1 kilometer divided by 3 minutes 20 seconds is our speed. So if I convert this, 1,000 meters is 1 kilometer, and 3 minutes is 180 seconds, plus 20, that makes 200 seconds. So we have a speed of 5 meters per second for the runner. So we can add this in here. So we'll have 5 meters per second. Initial position, be careful, this one is not 0 because of the choice we've made for the initial position or the initial time. So we can find the initial initial value for the position of the runner just by understanding that already 2 seconds elapsed by that moment. So we'll have Vrx times 2 seconds. So you can see, 3 seconds. So we have right away that in here we'll have 15 meters. So this means that the runner has a head start of 15 meters by the time the cyclist starts. Okay, and then we can go on the other side and do that same kind of analysis. So the initial position of the cyclist will just be 0. Final position of the cyclist is actually what we're after. Initial velocity of the cyclist will be equal to 0. It's starting from rest. We have the final velocity of the cyclist, which is unknown. The acceleration is given in the question. So we know that the acceleration will be equal to 2 meters per second squared. And the delta t is also an unknown quantity, but it's the same as for the runner. At this stage, the key step is to understand that at the moment the cyclists reach the runner, this means that they are at the same position at the same time. So that these two quantities will actually be the same at the moments that we're interested in, and these delta t, of course, will also be the same. So we will be able to set up an equation for the position of the runner at time 1, and then we'll do the same for the cyclist. And once we have these two equations, what we want to do is just to ask that the position of the runner is the same as the position of the cyclist. And that's what we'll do in the next segment. So we are now ready to solve. We'll need 3 equations for that. The first equation, the equation of the runner, will just give us the final position of the runner based on its initial position, its velocity, and the delta t. Okay. In here, I can already replace a bunch of values if we want to. We know that the initial position of the runner is just 15 meters with the convention that we used. Then we also have that the velocity of the runner is 5 meters per second, and the only unknown in this equation on this side is the delta t, and the final position of the runner on the other side. For the cyclists, similarly, we want to find the final position of the cyclist. We'll use the t-square equation for that here. So we have initial position of cyclist plus initial velocity of the cyclist times delta t plus 1/2 times the acceleration of the cyclists times delta t squared. And a couple of things will simplify in here. The initial position is 0, the initial velocity is also 0. So our equation will become slightly simpler. We'll just have that the final position of the cyclist is equal to 1/2 times the acceleration of the cyclist times delta t squared. And the acceleration of the cyclist we know is 2 meters per second squared. So this means that in this equation in here, we'll have 1 meter per second square, just taking the 2 and dividing it by 2. And then we have delta t squared. So that's our second equation. And as we were saying, when the cyclist passes the runner, this means that their positions are the same. So what we have in here is an equation, and the equation will be that 15 meters plus 5 meters per second delta t is equal to 1 meter per second square times delta t squared. So we have a quadratic equation with only one unknown, delta t, so we just have to solve this equation in order to find our missing time. So we can rewrite this equation. We have 0 is equal to 15 meters plus 5 meters per second delta t minus 1 meter per second square times delta t squared. And from this we can calculate the value of delta t using the quadratic equation. So we have delta t is equal to minus the b term, which is minus 5, plus or minus square root of 5 square minus 4 times the acceleration, or the a term, I'm sorry, in here, which is minus 1, times the value of the c term, which is the 15. All of that divided by twice the a term, so 2 times minus 1. I'll let you calculate the root, but you should get either minus 2.11 seconds or plus 7.11 seconds. Not surprisingly, we want to keep the positive time, so we have that delta t in here will be equal to 7.11 seconds. That's the time after during which the cyclist will speed up so that it can catch with the runner. So let's use this to answer our questions A and B that we had previously. So now that we have the time, we're ready to answer how far will the cyclist need to travel before reaching the runner. So we have our equation in here, so we'll just plug in the numbers. A is 2 meters per second square, and then we have the 7.11 seconds that needs to be squared. And the answer that we'll get from this is 50.55 meters. And not surprisingly, you could also have used the equation for the runner to find that information. Remember, the initial position of the runner at the moment the cyclist started was 15 meters. And then we have the velocity of the runner, which was 5 meters per second. Time is still 7.11 seconds. And we would get, once again, the same value, so 50.55 meters. So that's the distance that is traveled by the cyclist while to catch up with the runner. And if we want to answer part B, which is asking for the speed of the cyclist at that moment, well, the final speed of the cyclist is just equal to the initial speed of the cyclist, which we said was 0, plus the acceleration of the cyclist multiplied by the delta t. So we'll just have 2 meters per second square, which is the acceleration, times 7.11 seconds, and that gives us 14.22 meters per second. Okay, it's hard to make sense of it to see if it's a number that is likely. So if we transform this into kilometer per hour, I'll let you do this one, but you should get 51.2 kilometer per hour, which is a bit fast, but it's not crazy. So this is the speed of the cyclist at the end. Okay, so our answer do make sense. They are in agreement with what we expected to see. So just be careful. You notice that the speed of the cyclist at the end is much bigger than the speed of the runner. Okay, so that's what we see whenever we have an object that is catching another one. The typical graphs that we will have are such that one of the object is moving at constant speed often, and the other object is speeding up because there's an acceleration. So at the end, the slope of the object that is catching the first one will be steeper, which means that it's going faster. Hope this helped. Thanks.